Hello, this is Dr. Muhammad, and this is another video under Design of Steel Structures according to AISC. Today I'm going to start with beams or steel beams, part 1. And the contents for today, I'm going to give an introduction first, and after that I'm going to talk about the flexural strength, and after that the bending stress and plastic moment, and then I'm going to give an example after that. Okay, let's go to the introduction directly. Okay, first of all, we want to understand what is the meaning of beams in general. So whenever that we think about beams, we are thinking about an element, as you can see, it is connecting between two vertical columns, which is something like, as you can see here, for example, and mainly it is loaded with in the vertical direction. So whenever that we are going to find how this beam is going to bend or going to deform, we're going to find that it is going to deform in this way, as you can see, because all the loads are coming vertically on the cross section, so it is going to be under flexural bending and it's going to deform in this way. Beams are structural members that support transverse loads. That's the key word here, transverse loads, and are therefore subjected primarily to flexure, okay, primarily to flexure or bending, okay. So why the word primarily here? Because sometimes there is some axial forces. So we are going to have some axial forces, but we are not going to consider them. We are going to neglect any axial forces because there is no single element that is going to be that does not have axial forces. But if it is negligible to the level that we can neglect it, then we are going to claim that this element, whether that it's a beam, for example, okay, if we're talking about beam, so this beam is going to be, to somewhere extent, it is going to have some axial load, but primarily it is loaded in a transverse or the support transverse loads, and therefore subjected to flexural or bending behavior. If a substantial amount of axial load is also present, the member is therefore or is referred to as beam column. Okay, and this is, we are going to talk about it later on. So in general, whenever that we have only beam that is under or subjected to vertical loads, as you can see, transverse loading, as you can see, we call this beam. Okay, but if we are going to see that this element is going to have substantial amount of axial force plus the flexural bending straining actions, in this case we are going to call it beam column. Okay, beam column, which is going to be discussed and explained later. Okay, so to this point we are now on the same page that we understand what is the meaning of beams. Okay, let's go next. So commonly, whenever that we are having the common used cross section, the common used cross section sectional shapes for beams include wide flange, standard I-beam, and M shapes, which is miscellaneous. So we have this is the commonly used cross sections for beams. Channels or channel shapes are sometimes used, as are beams built up from plates in the form of eye or box shapes. Okay, sometimes we can use channels, okay, for the for beams, but commonly the most common shape that is commonly used is, as I said, the wide flange, okay, and standard eye or standard section, and the miscellaneous shape. And for reasons to be discussed later, doubly symmetric shapes such as standard rolled, wide flange, M, and S shapes are the most efficient. So we are going to find that we're going to talk about this later, that is the doubly symmetric shapes. They are considered to be the most efficient shapes for beams. Okay, so this is the common kind of shapes that is going to utilize or fully utilize the beam like capabilities. Okay, let's go now to see where the beams are covered in our AISC specification. Okay, so coverage of beams in the AISC specification is spread over 2 chapters. So we have 2 chapters here. The first one is chapter F, which is, you can find it titled with Design of Members for Flexure. And the second chapter is chapter G, which is Design of Members for Shear. Commonly, we are going to encounter these 2 main straining actions whenever that we are designing the beam, flexure and shear. So we're going to find flexure in chapter F, okay, and design for members for shear. We're going to find it in chapter G. So this is the most frequently visited chapters whenever that we are talking about beams when it comes to the specification of structural steel building code. Okay. Now let's go to the next part, which is related to there are like 2 main categories for the shapes that we commonly used for beams. The first one is the hot rolled I shape, is the most commonly used for beams. Okay, this is the hot rolled. This is based on the manufacturing process itself. Okay, this is a hot rolled doubly symmetric I shape. As you can see, this is manufactured as we said. This is the method of manufacturing for this. It's the one most commonly used for beams. The other one is this one, which is the welded doubly symmetric built-up I shapes. Okay, welded shapes usually fall into the category classified as plate girders. We're going to find this whenever that you are going to design for bridges, for example. You're going to find that the standard hot rolled shapes are not going to be sufficient for fulfilling the requirements or to stand against the required straining actions. So we are going to make build up section. We're going to give or bring some plates and weld them together in a certain way, and we are going to have whatever the height that we want and whatever the width that we want, and we can provide the available strength required for our case. So these are the most commonly used types. Commonly this shape, which is the built up, you're going to find it especially in bridges, for example, or non-building structures like offshore structures and other industrial facilities or petrochemical facilities and so on, whenever that we need special cross sections. But in buildings, you're going to find that we are using hot rolled sections commonly. Okay, for the built up sections, we have different types as well. We have like long span. Okay, this is cover plated beam, plate girders, truss beams, castellated, which is honeycomb beam, something like these shapes. They are going to be also for the we call it for the long spans. We can control everything for it. We have tapered beam to reduce beam depth where moment is small, something like this. Whenever that we want to, we know that the moment is going to be small at this position, but it's high here. We are going to have tapered one. Cover plated beam, attach plates to flanges where moment is large as well. In some places we can put additional plates in order to have more moment resistance. And honeycomb beam, cut web of wide flange and weld them together. This is to reduce the amount of steel used in general. Okay. In a typical floor system, you are going to find that beams or girders are horizontal members supporting slabs. So we're going to find that we are like having, these are considered to be our beams, which is like taking the amount of dead load and live load and whatever, okay, from the slab, and then this load is going to be transferred to something we call it girders, which is like beams also, but with like larger cross section. And these girders, they are connecting between the columns. So we are having like secondary beams, and then we have like main beams, we call them girders, which are connecting between the columns. Okay. So these beams or girders are horizontal members supporting slabs. As we said, they resist both gravity and or lateral load. Girders span P over W. Columns, beams span P. Sorry. Girders span between columns and beams span between girders. Okay, so this is like how we can like differentiate between beams and girders. So we can call this as this is beams, okay, and this is, we can call it as girders, okay, or we can say this is the secondary beams and like primary beams. Okay. Okay, so this is actually, yes, this is how the floor slab spans between secondary beams as we put it here. Okay. And this is the primary beam. Okay. So commonly the length of the beams are like ranging between 6 to 12 meters, okay? And the span of we can say these secondary beams are ranged like from 3 to 4 meters, and the girder spans like from 6 to 9 meters. This is the common ranges, okay? This is the common ranges for us. Okay. Now we can like talk about the beams from the connection point of view. So girders can be either moment connected or shear connected. Moment connected or shear connected. Actually, whenever that you look to the end of the beam, you are going to find the type of the connection is going to give you like a hint whether it's a moment connection or shear connection. For example, something like this. This seems to be like a moment connection where that we are going, or we are expecting moment to be resisted here. Okay, similar here as well. Similar here. They are like all of them. We are going to find that there are like compression and tension going to be developed if we are having flexural straining actions on the beam, and these fasteners are going to work to resist the end moment of the beam or the girder. So, and this is something similar here, that we are going to have some like compression and tension in the upper and lower flange based on the type of the moment at the end, and we are going to tell that this is like moment connection. So moment connection means that moment is going to be transferred from the end of the beam to the column. Okay. On the other hand, we have another type which we call it shear connection. Shear connection means that there is no moment is going to be transferred from beam to column. Only like the gravity loads or the vertical loads is going to be transferred from the beam to the column through this connection, like some bolts here or maybe some line of weld, and that's it. So there is no moment is going to be developed here. So we can like categorize beams based on whether it is moment connected or shear connected. Okay. Another thing, whenever that we arrange the steel beams in a floor, it is connected to slabs through what we call it shear studs. Okay, this is going to make, this is embedded shear stud connector. This is commonly, you can find it very large whenever that we're talking about the bridge decks and so on, you are going to find that these are the shear studs, and you are going to find the concrete deck is going to be poured on it, and then this shear stud or embedded shear stud connector is going to transfer the loading on the concrete deck through shear flow to the steel girder, as you can see here. This is a common way you can find this commonly on bridges. Okay, so this is how it works, that there is a shear flow, okay, or shear transfer at steel concrete interface that is going to make the steel beam work compositely with the concrete deck. Okay. Sometimes we can find open web beams, as you can see here, very large, okay, circular hollows here. This is actually to allow any kind of, first of all, in order to reduce the amount, and also it is going to be good for any surfaces to pass through holes. These holes are going to be very useful for any kind of like HVAC or cable trays or something like this, if you want to say. As you can see here, we have like pipes are going through these holes, so they may be weaker in shear, okay, but they are going to be very good for carrying only gravity or whatever the roof, and then transfer it to shear connection to the main girders, as you can see here. Okay, so this is like, these are common shapes that you can see in different places. Okay, at the end you are going to find something like this also, that whenever that you look, especially in garages, okay, and warehouses and so on, you're going to find that they are making like spray fireproofing using a gypsum-based plaster to provide layer of insulation to retard heat flow into structural steel elements. This is a common thing that I think that you can see it in garage, especially garage, as you can see, in warehouses and so on. Okay, so this is only for like fireproofing. Okay, now let's go to the things that is related to our design. We're going to start with the structure, or the flexural strength. Okay, so first of all, here we are going to focus on flexure. Okay, we're going to focus on flexure. Shear will be covered later. We are going to cover the shear later on. The required and available strength are moments only, because we are talking about beams, okay, whether they are like continuous or not. So we are talking about a type of moments at the end. We need to know what is the available moment, what is the required moment, and we are going to compare the both together. And we are going to find that shear is going to be checked later on. Especially for beams, we are highly concerned with the flexural moment. This is our main concern. We want to fulfill and be sure that the flexural moment is going to be okay. After that, we are going to check other things, which is, for example, shear or deflection, okay, vertical displacement or drift or something like this. But our main concern in beams always is flexure, okay, moments. So in this case, we are going to, for load and resistance factor design for LRFD, we are going to find that the most repeated equation for us is M ultimate on the left, which is, this is the, what we call it, the required moment, right? The required moment strength, which is coming from our load combination, okay? This is coming from our load combination in AC 7, for example. It should be less than or equal to phi b, which is going to be the resistance factor. This is the resistance factor related to the bending, okay, or flexure. And this is commonly in flexure, we are going to take it 0.9, okay, and then multiplied by mn, okay, which is the nominal moment strength. This is nominal moment strength. Already we are going to give the explanation here. So the nominal moment strength. So this is the definition of whatever, or these are the equation, the simple equation that we want to take into consideration for us. The right hand side here, this right hand side, we call it like this: design strength or design moment. Both are okay. So phi b times mn, we call it design strength or design moment. Okay. However, that the left hand side of the equation, we call it the required moment strength, which equals to the maximum moment caused by the controlling load combination from ASCE7. Okay, so this is how we can work with the flexural strength, okay, with LRFD. Okay, now let's go to ASD. So for allowable strength design ASD, it's very simple. We are going to have the same equation. On the left hand side, it is the required moment strength, which equals to the maximum moment corresponding to the controlling load combination from ASCE, right? This is the left hand side. The right hand side is going to be the nominal moment strength, which already we have explained in the previous slide, and it is divided by a safety factor for bending. For bending, it is going to be 1.67. Okay, so this is for bending, it is going to be the safety factor, it is going to be 1.67. Okay, this equation we can put it, okay, in another form easily for us to get, so, or easily to understand. So instead, it is nothing like we are going only this mn, we are going to put it instead of mn over 1.67, it is going to be 0.6 mn. And if we are going to like divide the two sides with the elastic section modulus, then we are going to have in the left hand side, we call it FB, where this FB, it is the maximum computed bending stress, and the capital FB, which is going to be the right hand side, it is going to be the allowable bending stress. So here it is the maximum computed, and this one, it is going to be the allowable bending stress. They are the same actually. Okay, we are not making anything. This is only we are dealing with moment here. However, here we are dealing with allowable stress, stresses. We are talking about stresses here. Okay, it is very similar if we were like using F over A. We were saying that this is the stress, right? Here we are talking about, instead of F, it is going to be M. Okay, M over the section modulus. So moment is related to the section modulus. However, that force is, in case of columns, for example, it was related to the area. Okay, so that's it. So there is no change here. Okay, whether that we are going to talk or we are going to use the moment or the allowable stress one, both are okay. Okay, so now let's go to the next part, which is bending stress and the plastic moment. This is an important thing that we need to like understand clearly. Before going and indulging into this part, I want to highlight what are the stages that the cross-section is going through whenever the load or the flexural straining actions are increased. Okay, so if we have a cross-section, as you can see here, which is like with the width B and the depth D, okay, and we assume that we are having a relation between the moment and the curvature. So in the horizontal axis here we put the curvature, okay, and the vertical axis we are going to put the moment. If you look here, you're going to find that this is the curvature moment relationship. It is very similar to the stress strain curve, right? We're going to find that in the very early beginning of this curve, we call that region or this part, it is the elastic part. As you can see here, this is the elastic part, right? Elastic. So we designated as A here. Elastic means that, what is the meaning of elastic? That the stresses that is going to be developed across this cross section is going to be, the strain is going to be always less than the yield strain. Okay, less than the yield strain. And of course, the stresses that is going to be developed always less than the yield stress, right? Okay, so if we say that this, what is the meaning of yield stress here and yield strain here? It is similar to yield moment. And if we have something here, if it's phi, for example, so it is phi yield. This is corresponding to yield. So whatever what we are having here in the elastic range, we are going to call it elastic. And the shape of the stresses are going to be allocated linearly, as you can see here. However, after a while, whenever that we increase the loading, okay, up until this point, which is yield, we found that the cross section or the behavior of the cross section after this point is going to be a little bit changing. We're going to find that the section is going to be changed to be elastic plastic section, elastoplastic section. What is the meaning of this? Which is the stage B here. We call it elastoplastic system or elastic plastic. What is the meaning? We're going to find that the fibers at the top and bottom, they are going to be yielding. Already they are reaching yield because here it is high stresses, right? So it is going to reach the yield. Here and here, the fibers are going to reach yield, right? And this means that our cross section is going to have some part of it reaching yield, okay, reaching yield and exceeding it as well. So this is the part of elastoplastic system. So it is going to increase. So every time it goes higher than M yield, the larger the amount or the larger amount of or larger area of the plastic section or the plasticity going to spread on the section. Okay. After that, we are going to reach to some level here. Okay. This level it is designated as MPL, which is plastic moment. Here it was M yield. It is yield moment. Okay. So at M plastic, okay, we are going to find something that is very interesting. We are going to find at this stage, which is stage C, the plastic section is going to be developed. The entire cross section is going to reach yield and exceed it. So as you can see here, look here, all the section already going to be reaching yield. Okay, so it is going to be in the yield level. Okay, this is what we call it M plastic. Okay, so these stages are very important for us to understand that the cross section, okay, the cross section, whenever that you look to the stress pattern or the strain pattern, you are going to find that the cross section going in the elastic range is going to utilize the whole elastic behavior of the section. After yield, some part of it is going to yield, and after that it's going to reach to some certain level where the entire section is going to be under yielding or going to be in the plastic range. Always F yield is going to be controlling the stress, is going to be F yield. The strains here is going to reach and exceed the yield strain. As you can see, we are going in this direction. So our strain is going to exceed the yield strain, or if we're talking about the curvature here. Okay, so this is how it goes. Let's understand it more in the next slide. So whenever that we have a beam and we have a load, as you can see here, concentrated, then the moment is going to be developed in this way. The maximum moment is going to be in the middle. Okay, the maximum moment is going to be in the middle, okay, or at the middle. So by increasing here in stage A, we say that our F, which is the stress in the cross section, the maximum stress is going to be less than F yield. And after a while, we are going to find that our cross section is going to reach F yield. Okay, this means that the cross section already, it is about to, some part of it is going to yield. Okay, after that, at stage C, okay, we're going to find part of it is going to be under plastic range, and we're going to find that the fibers at the middle of the beam is going to be, as you can see here, it is something like this, like the fiber yielding top and bottom. Okay, and then after that we're going to the last stage, where that in this last stage the additional moment required to bring the beam from stage B, which is this stage, okay, which is the elastic, to the next stage, to stage D, which is this stage from here to here. Here it was under yield, here fully yielded. So the stage B to stage D, that the moment, as we said, required to bring the beam from stage B to stage D is 10 to 20% of the yield moment. 10 to 20% of the yield moment, M yield, for the wide flanges. When stage D has been reached, any further increase in the load will cause collapse. So after that, the system is going to collapse. The system is going to collapse. Since all elements of the cross-section have reached the yield plateau of the stress strain curve, an unrestricted plastic flow will occur. Okay? That's the point that we have been discussing before that. After that, there is nothing here would happen because collapse would take place, mechanism would take place here. A plastic hinge is said to have formed at the center of the beam, and this hinge, along with the actual hinge at the ends of the beam, constitute an unstable mechanism, because here we have hinge, at the other end we have hinge, and in the middle there is another hinge. What is the meaning of hinge or plastic hinge? It is a point where that moment cannot be transferred from the right to the left and vice versa. It is as if it is like internal hinge is going to take place here. Okay? Okay, so let's go and see what is happening whenever that we are reaching the plastic hinge, or this stage, which is stage D. We found that the plastic, if we're going to look to the cross section here, we found that F yield is going to be developed across the whole section, the top and bottom fibers, and it is going to be equal here. This is the amount that can be resisted. The stress can be resisted by each fiber, whether in the flange or the beam. It is going to be the same. F yield is going to be the same. F yield is going to be the same. Look back here, maybe the stresses are going to be the same. However, if you are going to talk about the strain, you're going to find that strain still they are having like gradual levels also. Okay, the strain is having gradual level, so it is the maximum the top, and then it decreases. Still it is linear, even that under the stress or the yield, stress is taking over the whole section. Okay, so we found that there is something is going to be developed here. Compression force is going to be developed in the upper half, which is going to be C equal to area, or AC, okay, times F yield. AC, it is the area of the compression half, and in the bottom we're going to find that there is tensile force is going to be developed, which is area under tension times F yield. The distance between the two should be A. Okay. From equilibrium, summation of x equal to 0, C must equal T. Tensile force must equal to the compression force. And after that, we are going to find that if this is C, as we said, it means that A under compression, which is the upper half times F yield, equal to area under tension times F yield. And as we know that F yield here and here, they are going to cancel out because it's the same entity, then we are going to find at the end that the area under compression must equal the area under tension. The area under compression must equal the area under tension. Thus, the plastic neutral axis divides the cross section into two equal areas. This is a very important concept for the plastic moment development. That the plastic neutral axis, which is related to dividing the cross section into two parts, one part under compression and another part under tension, we found that it is, or it must have, area in compression equals to area in tension. They should be the same. Okay? Okay, that's an important concept. We're going to use it shortly in a minute. Okay, based on that, let's develop MP now. We want to get M plastic. What is the value of this M plastic? Okay, as we said from our analysis before, we know that there is compression force and there is tension force is going to be developed. All the cross section is going to be under F yield. Okay, our M plastic is going to be the resistance of our system, or the resistance of our cross section. It is going to be F yield times AC, which is this compression force, times this A, which is the distance between the compression and tension. Okay, and this is of course across the plastic neutral axis. This can be repeated again, but instead of using AC, we are going to use AT. Everything is the same, but we're going to change AC with AT because they are the same from previous slide, as we said. Okay, this is what we have obtained in the previous slide. So in this case, we are going to say this equals to F yield times A over 2. What is A over 2? It is the total area of this cross section, the total area. A over 2. So A over 2 equals to area in tension equals to area in compression. Okay, times A. Based on this, we can say F yield, it's alone here. And then Z, we're going to give it a name here. We call it the plastic section modulus. It equals to A over 2 times A. Okay, A, it means the area. A, it is a distance, okay, as you can see. So our Z, okay, A and Z should be given designations. So we have A, which is the total cross-sectional area, and small a, it is the distance between the centroids of the two half areas, the centroids, okay, the distance between the centroids of the two half areas. And Z, we're going to give this name to Z, which is half of the area times the distance between the two forces. And we are going to give it plastic section modulus title. This is the name of it, okay? Plastic section modulus, okay? Remember that the plastic section modulus is different than elastic section modulus. I'm going to show it in a minute now, okay? Plastic section modulus equals to half of the area times A, where is A is the distance between the compression and tension centroids. Okay, the centroid of each half is going to be, or the centroid, the distance between the centroids of the upper and lower half multiplied by one of the forces, whether it's tension or compression, is going to provide for us the plastic moment. And our plastic section modulus is going to be, as you can see here, half of the area times the centroidal distance between upper and lower halves. Okay, so now let's go and try to find a relation between the elastic and plastic section modulus. The elastic and plastic section modulus. Okay, so now let's have this cross section here that we have here, which is rectangular cross section with widths B and D. And we are going to assume that it is in the elastic case. So we are going to say that the stresses are linear, okay, and neutral axis is going to be in the middle. And we have the same cross section, okay, with B and D, but we are going to assume that it is in the plastic case, fully plastic case. So we are going to find that our neutral axis is still in the middle, and we are having the distance between the two blocks, compression and tension, as you can see here. Starting from the beginning, you're going to find, first of all, neutral axis, as we said, whether for elastic or plastic modulus or elastic or plastic sections, it is going to be in the middle. Here, because we have a triangle, then the centroid of the upper half for the forces is going to be, we call it C. This C is going to be the area of this rectangle multiplied by the width, right? So it is going to be half F yield, because we reach F yield. This is the base of the triangle, times D over 2, which is the height of the triangle, times B, which is the width of the cross section. So it is going to be F yield dB over 4, right? This is the force here, compression force. And we are going to find that the tension force is going to be the same. Okay, if we are going, because the same area applies here. Okay, the same area applies here. It is the area of triangle. So here we are going to find that M yield, in our case, is going to be the force, whether it is the tension or compression, times the moment R. The force, in our case, whether it is C or T, okay, it is no problem here. They are the same. Right, times the distance between C and T. It is 2/3 D, because we are talking about triangles here. So it is 2/3 D. The final M yield is going to be like this: F yield BD squared over 6. Repeat the same for this section under the plastic case. Okay, you're going to find F yield is going to form a rectangle here and rectangle here. So this means that our C is going to be the area of this rectangle times the width. So it is F yield times D over 2 times B, right? Which is equal to F yield dB over 2. Similar for the tension, it is going to be F yield dB over 2. And the distance between the two, it is the distance between the centroids. Take care, it is going to be half D, half of the distance, because it is the center between the centroids of rectangles. This means that our M plastic going to be the force times the lever arm, and here it is going to be T times D over T, or C times D over T, both are okay. T and C, they are the same, which equals to F yield dB over 2 times D over 2. This gives us F yield BD squared over 4. It's very similar to this, but instead of over 6, it is over 4 here, right? This is the difference. This is plastic moment. This is yield moment. This is plastic moment. Okay. Based on this, we can write the relation between elastic and plastic modulus, which we call it shape factor. We call this the shape factor. So if you are going to give the ratio between the two, you are going to find that M plastic over M yield, M plastic over M yield, it gives to you almost 1/2. Whenever that we're talking about rectangular cross section, okay, whenever that we are talking about rectangular cross section, remember M plastic equals to F yield times Z, and M yield equal to F yield times the elastic section modulus. F yield cancels with F yield, and we are going to remain with Z over S. Z here is BD squared over 4, S here equal to BD squared over 6, and then we're going to end with 1.6, 1.5. What is the meaning of this? This means that the plastic section modulus is going to be 1.5 times the elastic section modulus whenever that we are talking about rectangular sections. That's the meaning here. So we're going to have almost like 50% extra bonus for us if we are going to use the plastic section models. Okay, so remember, well, this is for the case of rectangular section. Then we need to know what is the case for other sections. Okay. Okay. So this is actually the shape factors. If we're going to talk about our wide flange shapes, it is going to range from 1.09 to 1.18. Okay. It is much less than 1.5. Okay, much less, because actually our area is concentrated at the edges of the cross section, not like the rectangular section. Okay, so in general, the shape factor, which is xi here, psi, it is going to be MP over M yield. This means that the ratio of the plastic moment over the ratio of the yield moment is going to be like we're going to utilize from 9% extra to 18% extra. Okay, 4 wide flanges. 4 wide flanges. Okay, so can see something like this. If we are going to draw a relation between phi over phi yield versus M plastic over M yield for different shapes, so we're going to find something like this. For I section, we are in the range of extra 14%. Pipes, like 1.27, so 27% extra. For rectangular section, as we said, it is 1.5. If we're going to have like solid tube, for example, then it is going to be 1.7. If we have something like this, then it's going to be 2. The more that we are concentrating our area toward the center, then the more that you are going to find the contribution or the extra of MP, okay, over M yield. So this means that if I ask you a question here, which case or which shape is the best in terms of M plastic, then of course this shape. Okay, and the I section is going to be the least one. Okay. Okay. The other case that we want to understand is, what if that we have unsymmetrical shape? If we have unsymmetrical shape, what is going to happen for us? So in this case, we are going to find that the areas above and below the neutral axis must be equal at fully plastic state, right? At the fully plastic state, we must have, because as we said before, do you remember I said that EC equal to AT, area and compression should equal to the area and tension. That is something that we are sure of. So we are going to say that in this case, for example, it's an example only, we're going to assume the first thing that we are sure, 100% sure, that A1, which is like white shaded here, equals to A2, which is like shaded with this color. Okay, so we're going to start with this A1 equal to A2, similar to what we have. This is the rule of thumb that we have already obtained when we were like developing. If we go back here, do you remember? Yes, this is the point where that we said that AC equal to AT. From the very first beginning, we mentioned that the area and compression should equal to area and tension. Okay, so in this case, we are going to equate A1 and A2, but we are going to assume that one parameter that is unknown for us, which is YN, the distance from the top of the bottom flange to the neutral axis that we do not know where it is. Okay, just we are going to assume it YN. Then we're going to develop everything based on this. We're going to say area 1 equals to the area of this flange. We know everything about it. And this part, which is going to be function of YN, we're going to say that it's 15 minus YN. 15 minus YN, as you can see, times 1, which is the thickness of the whip, equals to the lower half, which is function of YN also, is going to be 8 times 1 plus YN times 1. This is one equation. In one unknown, we can obtain YN at the end, right? We can obtain YN at the end. Based on that, we can get the plastic section modulus for this section equal to this value, 228 inch to the power 3. Okay, So this is how we are going in case of unsymmetrical shape. Unsymmetrical shape. Okay? Is it clear? I hope that everything is clear for you, and I think that it's easy up till now. Okay, let's have an example, and then we're going to wrap up our video for today. Okay. So we are going to have a built-up shape. For the built-up shape shown in this figure, okay, we have like web with ½ inch, height of 1 foot, and the width of the flange is 8 inches, and the thickness is 1 inch. Determine two things, A and B. For A, the elastic section modulus, which is S, and the yield moment. So we want S and M yield. So this is the first thing, S and M yield. And the second is we want the plastic section modulus, which is Z, okay, and of course the plastic moment, which is MP, for the same cross section. This would give us a very good comparison between the two for our shape, how much S and how much M yield and how much Z and MP. And we are going to compare these results against one another at the end to understand how much that we're going to benefit from the meaning of plastic section and plastic moment. Okay, first of all, because of symmetry, our section is symmetric, right? So the elastic neutral axis, the x-axis, is going to be, as you can see, x-axis is located at mid-depth of the cross section. It is going to be mid-depth of the cross section, okay, which is the location of the centroid. The location of the centroid. The moment of inertia of the cross section can be found by using the parallel axis theorem. Okay, do you know the parallel axis theorem? It is easy actually. You are going to find here from this table. Okay, we summarized it here, or the textbook it's summarized here. So first of all, we're going to look to the component that we are talking about, which is the flanges, for example, 2 flanges and 1 web. Okay, so we have like 1 flange, another flange, and web, and then we're going to have the summation. So this is the inertia of each item, which is for the flange, for example, it is going to be 0.667. You can check it by yourself. We have the width and we have the depth. So it is going to be 8 times 1 to the power 3 over 12. You are going to find it for the upper and lower flange. They are the same. For the web, you can get it with the same technique. Then you are going to put in another column the area of each element. Okay, we neglect the area and the depth of the area and the distance of the web because it is going to be, it's not going to add very much for us. Okay, so here the parallel axis theorem, I plus AD squared, so are going to have the after having the D and A, you are going to add A times D squared with this I, and then you're going to obtain the inertia of the upper flange and the inertia of the lower flange, or the second moment of area around the neutral axis, and you are going to have the summation here. Okay, it is an easy calculation, I think, for you. You can understand it very well. So from here we can obtain our elastic section modulus. Our S is going to be I, moment of inertia, over the C, okay, over C, which is the furthest distance from the neutral axis. Our I here, it is 749.4 over C. It is going to be like this distance here. We have 1 inch plus like 1 foot over 12 because we're talking about inches. So 1 inch plus 12 over 2. 12 is 1 foot. Okay, so this gives us 107 inch to the power 3. And based on this, our yield moment is going to be, okay, M yield equal to F yield times S. Our section is made of steel with yield stress equal to 50 times S, where already we have obtained. It gives us 107, then the amount of the yield moment is going to be 446 foot caps. Okay, so the answer is the elastic section modulus is 107 inch to the power 3, and the yield moment is going to be 446 foot caps. Okay, now let's go to the second part. We want to make the same, but for the plastic moment. So because the shape is symmetric about the x-axis, as we said, our shape is symmetric around x-axis. Okay, so for the case of the section modulus, for the plastic section modulus, we're talking about area are going to be the same. So this is x here, area is going to be the same. So this axis divides the cross section into equal areas and is therefore the plastic neutral axis. We call it the plastic neutral axis. It's different than the, actually commonly it should be different than the elastic neutral axis, but here it is going to be the same because the plastic and elastic neutral axis would divide the whole cross section into two equal parts. The centroid of the top half area can be found by the principle of moments. We're going to obtain it by the principle of moments. Taking moments about x-axis, the neutral axis of the entire cross-section, and tabulating the computations in this table, you can obtain y bar. Okay, so you are going to find that we have two components here, which is related to the flange and the web. Okay, so we are going to have the principle of moments. So we have area, okay, and the distance of this area from the plastic neutral axis, which is y. So we have 8, okay, 8, and we have 6.5, which is going to be related to the, this is ay. We're going to multiply a times y to give us this value, okay, which is, as we said, like the first moment of area. This is the first moment of area. We're going to obtain the summation of area and the summation of the first moment of area values together, and we are going to divide them together. So divide one by the other. So it is going to be 61 over 11. It gives us 5.54 inches. What is the meaning of this value? The meaning is the location of the compression force and the location of the tension force is going to be distant from the plastic neutral axis with 5, which is y bar, 5.542. So how we got it? Again, we are obtaining the area and the distance of this area to the neutral axis. We multiply the area by the neutral axis distance. We call it the first moment of area. And then we have the amount of the flange, the web. We're going to make the same. Then we're going to tabulate the data, as we said here, for the flange and for the web. And based on that, we are going to obtain y bar. This is y bar here. Okay, as I said, this y bar is like giving to us the distance from, because we have the neutral axis here, the point where that the first half is going to be located. This is the tension force. Here is going to be the compression force. Okay, so this distance from the plastic neutral axis is going to be y bar. Okay, so we have now y bar for compression and for tension, and then we can go through the remaining parts to obtain the section modulus and the plastic moment. Okay, so our which is the distance between the compression and tension, is going to be 2y bar, right? 2y bar, it gives us 11.09. And that plastic section modulus is, our plastic section modulus, if you remember, we said that our z equals to half of the area times the A, which is the distance between the two, as if that we are taking this area, okay, times the distance from here to here, which is A, okay, and actually this is right here. Half of the area times the small a. Then the plastic moment is going to be M plastic is going to be F yield times Z, 50 times 122, which is already obtained from the previous step. This gives us 508. So Z is going to be 122 inch to the power 3. M plastic is going to be 508 foot kips. Okay, now let's go to the last step here, which is going to be related to the comparison between the sections. For our case, we are going to find the section models was 107, elastic section models. The plastic one is 122, higher than it. Okay, you're going to find it, as we said before, it should be between the range of 1.09 to 1.18. Do you remember this? Okay. And then M yield is going to be 446 here. M plastic is 508. Right? So we're going to find also that it is within the range. This means that using plastic moment is going to have or going to utilize additional capacity of the section compared to the yield moment. This is very important concept that we're going to explain later when we are differentiating between the different shapes, the compact shape and non-compact shape and the slender, especially between non-compact and compact. Okay, you're going to find that plastic moment is going to be controlling here, the controlling limit between the two, or the moment, or the yield and the plastic moment, the yield moment and the plastic moment. So anyway, this is a very good example for us. I hope that you can understand it well, and I hope that you can, from now on, for any cross section, whether it is symmetric or not, you can derive your own plastic or the plastic section modulus of the section and the plastic moment. You can obtain it well. This would bring us to the end of this video. I hope that you have understood what I have explained today, and see you in the next video. Thank you and see you later.